Hello, everyone. I'm Seraphim Alvanidis from Northumbria University in the UK, and I'm chairing today's webinar between the GIScience Research Group of the Royal Geographical Society and the GIS Research UK Network, who organized the annual GISL conference. It is a great pleasure to have with us today Dr. Clio Andris, Associate Professor with the School of City and Regional Planning and the School of Interactive Computing at the Georgia Institute of Technology, and also the Director of the Friendly Cities Lab at Georgia Tech. The talk will last around 40 to 45 minutes and will be followed by questions and answers, and we invite you to post your questions at the chat box. Thank you, and over to you, Clio.
Wonderful. Thank you so much for having me. So my talk today is entitled New Metrics, Software, and Geovis Tools for Geosocial Network Analysis. And I would like to thank all my co-authors who are part of this research for helping me develop it today. And describe two quick case studies. You may have seen some Mafia stuff before, so I'll mention that. And then the Thrive Network, which is in Southwestern Virginia. And then I'm going to describe a spatial social network analysis initiative called SNoMaN. We haven't decided what exactly it stands for, but we're still working on that. And then I'll talk about our tutorial for a new package called Spatial Social Network Tools, SSN tools. And today I'll demo our SNoMaN software, which does stand for Social Network Mapping and Analysis. And that is free open source web-based software where you can analyze your own social network. So the geospatial analysis of networks. A lot of times that geographers see networks, what we have is we're used to seeing a lot of infrastructure or road networks. I really like this one because it's John Snow's cholera map, but instead of just assuming people went Euclidean distance to the pumps, this one incorporates the road network and uses sort of a Voronoi polygon nearest where the nearest pump is on the road network. We also do a lot of geospatial analysis of networks, flows that are not necessarily on transportation. So this is great new software called Flow Mapper by our colleague Chalar and his team. And it's really nice to see geospatial networks being able to be visualized in geographic space using this software. So what I'm really interested in is about small social networks. So this over here is the first sociogram, and a sociogram is what we call a visual network of nodes and links in social network analysis. This is by Jacob Moreno, and this is a first grade class. So there's 21 boys in the class, and there are 14 girls in the class. The boys in the class are triangles and the girls are circles, and the edges between them are directed. So from this, we see that there's a few emerging high degree nodes. And let me just say that the directive edges are who was playing with whom and who nominated whom to be like their friend. And so we see a high degree node here of girl having a lot of connections, but we also see a process called homophily, in which case the kids of different genders are tending to connect with each other. So I like to think of these as really exciting features for geography and to see how we can put them on maps. So today I'll go over two case studies. One is about the American Mafia, and the other one is about a food sharing network in Southwestern Virginia. So in the 1960s, there were mafia networks in the United States, and the US Senate was very interested in capturing these networks. So in our network, the node are mafia members and edges are mafia members' criminal associations. And these were derived from a Senate investigation to find more about the mafia members. So the source is archival data from the Bureau of Narcotics dossier. And here's an example of one of the mafia members. And these is from one of the dossiers. This is Big Frank. And it says when he was born, It says where he resides, so it gives a home address for him. It also gives some locations like the Cuckoo Club, the Hula Hut, Java Club, etc. It talks about his family, and it also talks about his criminal associates. So we're really interested in the location, where he lives, and also the criminal associates. And from this, you can derive a network of where the edges are and where the nodes are, because the criminal associates also have household locations. So the network that is derived from these dossiers is driven by families. So in this diagram over here, in this sociogram, which was created in GEFI by our collaborator Dan Della Posta, the colors represent the different family that the node is in, and the size of the node represents the degree. So that's how many connections they have. This network has 680 nodes and 2,699 edges. The degree ranges from 1 to 77. So that means that the highest degree member in this network, who is John Ormento, has 77 different connections. This network is not directed. So meaning that the edges, if A says that they're connected to B, B doesn't necessarily need to say that they're connected to A, because there's no arrows on these edges. And then the average path length, which is how many hops it takes to get from one member to another member on average, is 3.88. So our goal was to map these members and to see what kinds of geographic aspects of their network were salient for us. So at the top here is the Mafia members mapped on the US map, and they are highly centered in New York. And so this is what they look like in the New York metropolitan area, where each dot is a Mafia member and each edge is a connection between them. These are some of the highest degree Mafia members over here on the left side. And then on the right side, we connect some of these high degree Mafia members with the mean center of their family. And we just did this for the New York families. We tried to test to see whether there was an interesting connection between whether the bosses and the high degree members tended to live in certain areas with higher income, or if they lived near each other, etc. We didn't find high correlations there, but from our visual exploration, we did find that a number of them lived near the water, and we thought that that might be to oversee some of the shipments that were coming in. So the new approaches that we wanted to describe here, the first one is called a cluster plot. And this answers the research questions, are families tight-knit socially, geographically, or both? And so from each of these dots on this plot, each of the dots represents one family. The bigger families have bigger dots and the smaller families have smaller dots. And on the y-axis, we have standard distance, which we're used to in GIS, whether something is clustered or whether it's dispersed. So how far do their members live apart? And then on the x-axis, we have something we call network density. And this is whether the members form a clique, whether they're all connected, or whether the members are disconnected. And the darker nodes here are just meaning that they are members of the New York family. So we found out that this fits like with the power law. So as the network is more dispersed, it tends to be less tight-knit. And as the network is more tight-knit, it tends to be also geographically clustered. We find some things that are off the trend, like New England, which had a number of members in Florida, and New England was just a little bit more spread out, even though they were pretty tight-knit. And then we also found that the Profaci family, even though that they lived very, very close to each other, they were not the members were not well connected, and a lot of the members were just connected to the boss. We also have a visual approach that we're using to answer a research question. Do powerful members live near the geographic center of their families? So here on this plot, color doesn't mean anything, but on the x-axis, we have the degree, and on the y-axis, we have the distance to the family median center. So from this, we can do some descriptive analysis. We found out that a lot of the New York families were sending agents to Miami, and because Miami didn't have a family that was dominating that area, and because Miami was a very lucrative place for importing cigars and alcohol and other items that came through there. And it was also popular for gambling. So a lot of New York agents went to Miami, and that's why you see this distance to the median family center being similar. But they had a varying degrees. So they didn't just send their highest degree members, but they sure didn't just send their lower degree members. Here's an example of a very high degree member that got sent to Miami, and that's Michael Coppola from the Genovese family. This Joe Bonanno, also known as Joey Bananas, he was sort of exiled, or he left his family in New York to go to Tucson, Arizona. So even though he had a number of connections, he's far from the mean center. And then these are 4 Genovese family members in California. So as you can see by this plot, there isn't really a clear connection between these, but it was good for descriptive analysis. So our final research question for this data set is, where are connected clusters located? So this map over here shows the New York agents and whether their closest connections are here in red, and we only highlighted the connections that are very, very close. So you can see that there's some areas where there aren't a lot of connections, and then you can see that there are some areas where there are a lot of connections. So from this research question, where are connected clusters located, we developed scan methods for spatial social network hotspot detection. So the way that these scan statistics work, they work just like our typical scan statistics in GIS, like our moving window statistics. So we have a focal window around a node, and we define that window. We can do Euclidean distance, Manhattan distance, or we can do K nearest neighbors. And what we would do traditionally is probably count, like do how many nodes are in here, and what would maybe another average summary statistic be. But what we're doing is a little bit different. We're finding how many edges are actually in the neighborhood radius. And then we're also calculating network density, which is given by this equation here. So this one is saying just how many edges fall completely within this radius. And then this one is saying, given the number of edges that are possible, given the number of nodes, how many do we actually have? And we'll show this in comparison with Geddes or GI star and a sensitivity test, because when you define this neighborhood differently, you get really different results. So here's an example of some of the output. We're sort of giving a different definition of hotspots given the spatial social network. So this is standard output for GI star, and we're using a 1 kilometer Euclidean distance neighborhood or focal radius size for this. And so the red squares are showing us where they found clusters of points. So this is a basic point pattern analysis that is fundamental for modeling point patterns. And so we find areas where they are statistically clustered. But then that we ran our methods, which are just descriptive methods, and we found that oftentimes the nodes that popped up as having a lot of edges between them, more than expected, we were able to find some different clusters. And so this was important to us because it showed us where there might be like connected cells of agents instead of just dots or agents that were not connected. So here's a little bit more. We're interested in the future and taking a look at more of the network motifs, but this is an example of some of the edge scan results using a 1 kilometer distance. And then this is an example of the node density results using that same distance. And from the map over here, the maps with the dark blue, we can see that there were some areas that were statistically significant for us, but weren't statistically significant using the GI star metric. And like any good GIS analysis, we do need sensitivity tests. So in our paper, we do show using New York City and also the city of Detroit, how our answers for the edge scan, the node density scan, and just how many nodes were had any edge at all, using these different sizes and these different definitions of neighborhoods. So that's a case study on the American Mafia. And the next case study is on the Thrive Food Sharing Network. So this paper is called Locality, Personal Ties, and Efficiency in a Food Security Network. So the Thrive Network is located in southwestern Virginia, and it's located near where Virginia Tech, which is a large public university, is located. And so this community created the Community Foundation of the New River Valley, which is this region, and they wanted to support nutrition and health in this area that has a high poverty rate and has issues with food security in some of their households. So my colleague, Jamie Kelly now, she collected a lot of information from these different organizations to see who was able to share perishable goods and non-perishable goods, so food, between different organizations. She also created a network based on which organizations were sharing information, client referrals, and other types of kind of social capital between them. So this one is called this is the New River Valley Community Foundation. And then this one is Feeding America of Southwestern Virginia. So those are big players in the network. You can also see things like the United Way. You can see some religious groups like the Giles Mission. And there's other things in here like the Virginia Tech Kitchen and like the elementary school, the YMCA. So these are the types of organizations that are participating in this network. And here they're sized by network centrality. So Jamie had locations for these, and so we wanted to work with her to ask some new research questions about this network. So the first research question here was on power situation and accessibility. So are better connected organizations, those with higher degree and higher network centrality, near points of interest? So our theory behind that would be that organizations that were sort of in the thick of things and were near other points of interest for like trip chaining, et cetera, might have more connections. And then our other question here is, are they near the geographic center of the network? So our networks with more connections and networks with a higher centrality, are they near the geographic center of the network? And I'll just pause here to mention that centrality is measured in a couple of ways, but it means it's sort of a metric of how important you are in the network in terms of connecting other people. So physical distance, our other research question was which nodes tend to connect to their nearest altars? And an altar just means their nearest, not an ego, so their nearest neighbors. And then local disconnection, which pair of nodes are nearby but disconnected? So we're going to suggest new ties between these nodes. And we're interested in this question because there might be organizations that are really close by, but because of the bottom-up nature of this network, it's a little bottom-up, it's a little top-down, they may not realize how close they are and the benefits of connecting with someone who's so close. So our metrics and our methods here. For our research question one, whether the different organizations are near POIs or near the center of the map, we created the mean and median center, distance to POIs, and we just did a Pearson correlation. The POIs were sourced from OpenStreetMap, and we removed POIs like park benches, recycling, cemetery, and mostly POIs that you could, we kept POIs that you could walk into, and we did a 1 mile driving distance to be considered near a POI. We performed this in ArcGIS and are using the iGraph package. The research question two, we developed a metric called K fulfillment. So this says how many of your K nearest neighbors are you connected to? So if you have 5 neighbors in the network or you have 5 connections in the network, how many of your 5 closest neighbors on the map are you connected to? So this is a integer divided by another integer to give us a ratio. And if the integer is 1, it means all 5 of your connections are also your nearest neighbors. The local flattening ratio is kind of similar, but instead of 2 integers, we get 2 continuous values. So this is the total distance to reach your K nearest edges divided by the total distance to reach a node's actual edges. So this is adding up the distance it would take for me to reach my K nearest neighbors. So it's just summing those up and divided by the total distance to reach my actual neighbors. So this can't get greater than 1, but 1 means that you are connected to your nearest neighbors again. We performed these in R. And then lastly, we have misconnections, which is saying which of your close neighbors on a map are you very disconnected to. You have that like 6 degrees of separation in the network. So since we are GISC people here and geo people, I won't go into detail too much about the nitty-gritty for power, situation, accessibility, but are better connected organizations near points of interest? Not really. We didn't find strong correlations there. And are they near the geographic center of the network using mean and median center? Also no. So I'll dig a little bit deeper into the answers to these questions. Which nodes connect to their nearest altars and which pairs of nodes are nearby but disconnected? And we'll suggest new ties between these nodes. So whose connections are very close and efficient? So this is a map of all of the organizations that participated in food sharing. So this is an example of the results of K fulfillment. How many K nearest neighbors are you connected to? And so if you see a white circle in the middle of the organization, it means that they're not connected to any of their K nearest neighbors. It means that if they had 10 connections in the network, or if they had 3 connections in the network, all 3 of those are not the ones that are most easily accessed on the map, or they're not the 3 most convenient ones to get to. So when you see a black dot here, it means that all of their neighbors are their most convenient neighbors. And so we asked what was going on up here in Perrysburg, and Jamie had told us that there was a priest who went around there and tried going door to door and creating these connections. So we see the result of that action here on the map. We also were asking why these areas here tended to have a higher K fulfillment value. Sometimes when you just have few neighbors in general and your K is low and you do actually connect to your close by neighbors, then you can have a very high K fulfillment. So in general, local connections between entities are uncommon in this network. So we use this K fulfillment metric to answer that question. Only 6 nodes are connected to their nearest neighbor. So only 12% of the network are connected to their nearest neighbor. And 30%, so 12 different nodes, are connected to either their first neighbor or their closest second neighbor. That means that these organizations are bypassing their most convenient neighbors to connect with other organizations. And 28 organizations had a K fulfillment value of 0, which means that none of their nearest neighbors they were connected to. And what that tells us a little bit about this network is that being close by is not necessarily correlated with wanting to have a relationship. And in fact, a lot of the relationships are from town to town instead of within the towns. So our question that we wanted to answer in a different way here was whose connections are very close or efficient. And so that is a continuation of the K fulfillment. So the global network flattening ratio for this network is 0.301. And the global flattening ratio is just simply the amount of distance it would take to connect everyone holding those degree distribution the same versus the amount of distance that it actually takes. And this is a kind of a stochastic method, so this can change a little bit, but it means that our network efficiency is at about 0.3. Unfortunately, we don't have a lot to compare that to. Like, is that high? Is that low? We've only done this with a few other social networks, but we're hoping as that distribution grows, we can situate our results a little bit better there. So the local network flattening ratio takes the total distance, and this is road distance in kilometers, to reach our K nearest neighbors, divided by the total distance to reach a node's actual K edges. So the results here range from very, very low, so that is beans and rice in Pulaski, and to very, very high, which is 1, meaning that they're connected to all their nearest neighbors. The mean here is 0.276. So the Giles mission has a low network flattening ratio. It connects to nearby nodes, but its flattening ratio is low because it connects with Feeding America. So that's one, not necessarily a drawback, but that's why we're doing K-fulfillment and the local flattening ratio, is because they can tell us slightly different things. Feeding America out here has a medium low K-fulfillment, but a high network flattening ratio. And that's really important because it seems like for a organization that has so many different connections and has so well connected, being out here can be a little bit, you're kind of asking like, well, that doesn't seem very efficient. They do tend to connect to a lot of their nearest ties and the ties that are most easily reached by on the road distance, but those ties are still quite far away. So even though it looks like most of their ties are far, it's still relatively efficient. So when we see a red dot here, just as to reiterate, it means that it has a high local flattening ratio, which means that the connections that it has on the given the distance that you have to travel to get to them are relatively efficient. But the ones what you see that have red here might still have a really low K-fulfillment value because even though on the road time it is pretty efficient, those aren't their exact nearest neighbors. So we like to have both when we're going over this map to describe what types of places are really connecting locally and which types of places like Pulaski out here or parts of Christiansburg, etc., do not have a lot of local connections. So our last research question for this case study is, where should new connections be made? And so we're calling this missed connections based on a old transportation sort of paradigm called the route factor, where the route factor, which we can model here as QIJ, is given as the number of hops that it takes to get from I to J, from any node I to J, and they call that a geodesic here. But we don't use that term a lot in our research because a geodesic has nothing to do with geography. So we call them kind of network distance or hops. Network distance also presents a problem, but. So this is how many hops it takes to get to your neighbor in the network, no geographic space involved at all. And then this is the Euclidean distance it takes to get from your one nearest neighbor to another. So here, when we plot these two values, and each dot here is an edge in the network, so it's not a node in the network, but it's actually an edge. So how many network hops does it take to get from one node to another? And again, that's not geographic at all, it's just in the sociogram, versus the log of distance between the two nodes. And so when we are taking a look at our results here, we want to know which kind of edges between organizations have a lot of hops between them, but do not, but are quite close geographically. So after going over this descriptively with our co-author, we found that the Blacksburg Farmers Market was featured prominently in a number of these cases. And so in the first case, they're quite near the elementary school, but they're entirely 6 hops away. So that's illustrated on the map here. The connection that they do not have here is in blue. So that's the distance between them. But the connections that they do have here are in red. So it does take 6 hops in the social network for them to reach, even though they're very close to each other. We also found that the Blacksburg Farmers Market and the Virginia Tech Kitchen had a lot of hops between them, but they were very close in geographic space. And then finally, the Blacksburg Refugee Partnership and the Farmers Market were also very close in geographic space, but they were connected. They had to do 4 different connections to get to each other. So from this and some more kind of chatting, we wanted to recommend that the Blacksburg Farmers Market potentially partner with some of these organizations because they're so close by, the elementary school, the kitchen for college students, etc., and maybe create some partnerships that would reduce the kind of number of intermediaries they needed to go through. And perhaps take advantage of their geographic nearness. So those are my two case studies that we focused on when we have a new social network from somebody who just does social network analysis and we map it, what kind of research questions can we ask and what kind of research questions can we answer? So now in the time I have left, I wanted to show you some really exciting, I think it's really exciting, software, a new R package that we're working on, and new open source web-based software that we're working on as well. So the first software is an R package, and this was developed mostly by Xiaofan Liang. And there should be a link in the chat, hopefully, or we can give it to you later, where you can access all of these things because they're live online. So we wanted to allow researchers to be able to implement some of the new metrics and new approaches that we were working on. So we wanted to create a spatial social network R package. And this one uses a lot of visualization. And one benefit of it is it connects iGraph with TMap and some of those packages pretty fluidly. So to install the package, you go with the dev tools here. That's just how it works. And we preloaded the data sets that we talked about. The Mafia nodes and edges are in there. We have restaurants in Atlanta that are geolocated in here. And then we have a synthetic emergency data set that's in here too. And I think the food sharing network has been loaded. So it comes with its own data. Some of the basic things that the R package users can use and to run the code here is to allow iGraph to calculate things like clustering coefficient, betweenness centrality, eigenvector centrality, degree centrality, which are very common metrics in the social network field. So the iGraph package will calculate those, and then you can map them using small multiples quite easily. And then we also have our more advanced SSN metrics that I described through the case studies. I didn't describe the linked activity spaces, but that one's also exciting. So with the advanced metrics, will help users to do their research, not just visually and not just interactively, but through better statistical analysis. So the hotspot detection, which we showed versus the GI star statistics, it allows you to calculate spatial social network hotspots using different radii, using different, like your K nearest neighbors, or using Manhattan distance, or using just Euclidean distance. And we like that the user can try these different parameters to look at how their results are sensitive to their input radius. So the package will make these different maps quite automatically. And this one is Atlanta points of interest data. So these are block group centroids and then restaurants that people in the block group centroids go to. So this answers the research question of where in the city do people tend to go to their nearest restaurant? And that those tended to be down in this area where we have that high network density. And then over in this area where we have a lot of restaurants, and down here, it tends to have a lower network density. So these are a bit sensitive to the number of nodes in your radius, but that happens. Okay, and then there's plots to explore sensitivity here. So you can take a look after you run it loop multiple times. You can take a look at how your results are changing based on your moving window size, your focal radius size. Okay, and now I'm going to turn to the SNoMaN software. So this is really exciting for us. We've been developing it from scratch. And Xichen Jin has been leading this and doing a really, really exciting job. So I'm going to do something I have never done before, which is a live demo over Zoom. But I think I'm among friends today, so we'll try it out. Okay. So the spatial social network software here, hopefully you can see it okay. All right. The spatial social network software here is available online, and it's built off a software called Argo Lite. And if you click this GitHub link over here, you'll be able to see the code to it. So we really are excited about open source. The first thing a user can do is load some of our sample data. So the data that we used in the papers is available here. We also have a flight network and some more experimental networks. So this network is similar to the food sharing network. This is in Blacksburg, Virginia. So it's very similar to the ones we just saw. And this one is actually a little bit different. It's on sharing information. So the connections aren't necessarily the exact same, but they're quite similar. So when you load this data, you get an analytics panel right here that automatically calculates the number of nodes, edges, etc. And I will demo how to load some data soon, if that's helpful during Q&A. The first thing that we wanted to see here was a centrality plot. And so we wanted to see if nodes on this graph, which are also here and also here in the sociogram, I'll just mention that the bigger nodes mean more connections and the color is similar. So the size and the degree is double encoding number of connections here. And here is that Feeding America, here's the YMCA, here's the New River Valley Community Foundation, etc. So if I wanted to see here, like, oh, hey, there's a node that's really far away but has a lot of connections, I'm able to brush it and then go and see which one it was and say, oh, this is Feeding America. It's a bit of an anomaly or an outlier on my plot. So I'm really interested in why that might be. To answer why that might be, Feeding America, even though it seems like it should move to the middle here, it also services Roanoke, which is a nearby large city. So it's a study area. It's a study area question. It's sort of a question of edge effects there. Or I might want to brush and select this node over here, and I find that that is like one of the big nodes of the community foundation, and I could move it around, and I can do it like that. Yep, live demo. Okay, so the next thing I wanted to show you here is that if I selected Feeding America again, and I wanted to see where their farthest edges are, I can take this edge distance distribution and automatically calculate, or it'll just show me where the most distant edges are. I can move it over here and find the medium distance edges, etc. Also, when I select things on the map, or I select things on the plot here, it automatically updates these network statistics. So that's really helpful. So the statistics panel is something that I'm really excited about. I'll show you it just implemented some of the things that we talked about in the PowerPoint. So running average distance and running shortest path will give me this route factor diagram. I'm gonna, oh, hey, the isolates are here. All right. Wow, I've never seen this before. Okay. Huh. You guys are good luck. Okay, so what I'm gonna do right now is I'm going to just show you how we do a hard reset. Here's the diagram. We'll resume the force directed layout. And you just have to click here and click here. And then we get that route factor diagram again. So I'm really interested in edges, so paths between these nodes that are really, really disconnected, but are really, really close together. So I click this here because I find that there's some edges. Each dot is an edge here, or each dot is a path. We would call this a path, where these two nodes are only connected, or they're connected by 5 intermediaries. So they don't have any closer connections. So something would have to, gossip or whatever would have to travel, or food would have to travel through all of these to get from one node to another, even though they are so close by. So then I would try to zoom in and find out where these two nodes were. They're highlighted in green here. So this node and this node are, even though they're really, really close by, they're separated by 5 different hops. And if I wanted to see which those were, what I would do is it's pretty easy to just go in and label these different nodes. So maybe there's another one here that I wanted to take a look at. And so we see something quite similar where they're separated by 5 different hops, but they're pretty close in the network. So that's an example of how to use the route factor diagram with this food sharing network. The next thing I'll show here is the Mafia network. So this one is also preloaded, and I do know that I've got about just a couple minutes left. So here's a really fun part of the software is when you just say resume force directed layout, and then you get the sociogram, and then this uses this uses common network, so a force-directed layout. And it'll kind of play around until it converges. I'll have to say the Mafia network is our least stable network on here because this software doesn't necessarily scale to really high values. So the first thing I want to do on this network here is take the nodes and change their color based on family, because I know that family is a really big deal in this network. And then I can take a nominal scale or nominal data, and I can automatically see that the different nodes on the map are by family, and then the different nodes on these clusters are by family. So I can either filter it, I could filter this data in a way where I choose the family, or I can filter the data just by touching it. So I will demonstrate here briefly community detection. We use something called the Louvain algorithm, which detects communities in this network without any regards to the map, but it will just detect where these clusters are in the sociogram. So it reports a Q value of 0.657, and that's a common value to report in social network literature. That's pretty high, I think. So then what we want to do is we may want to have the convex hull around some of these communities. I'm actually going to cheat a little bit and do the convex hull around each family because, spoiler alert, the family and the communities are quite similar. So this creates a convex hull around the different dots. The convex hull will remove outliers that are really far away. Otherwise, the whole network or the whole map can look like shards. I'm going to turn off the edges here so we can see a little bit like how these families are outlined and what their kind of bounding box is. So if I wanted to select maybe Chicago, I could log out. I just selected Los Angeles, but if I wanted to take a look at Chicago, I could zoom in here and see the radius and the bound or the convex hull around them. Again, we exclude some major outliers there. But this is exactly what we showed in the slides as a method for this cluster plot. I really like it because you can see why certain networks might be more scattered than others. For example, this Buffalo network had a number of people in New York and in Miami. And so we get that from knowing that the standard distance is really high here, but now we can see from the map why that might be. Okay, and then I'll show you my last part. This is not a social network, but it's really fun to work with in the software. So this is a flight network that's free online, and you could just load it right here from our file. It's ready to go. And so each dot here represents an airport, and I'm using the same kind of color scheme that I talked about before with the nodes one color, or the redder nodes are the one color, and then the lower degree nodes are a bit smaller. So in this network, this is really fun. Here's the centrality plot for it, so we can automatically find some high degree nodes, etc. I really like this network because when we resume the force-directed layout, we get a bunch of these kind of tails out here. And that was really interesting for us to see, like, these chains. So we wanted to see where the chains were, and we learned that Alaska has a number of flight system that isn't really hub and spoke, but there used to be mail planes out there, and they create chains there. So that's really interesting for us. And we also can do our modularity here, run community detection on the network, and we can see the different communities pop out. Alaska gets a bunch because they're so disconnected, and then this is a different community. We found a number of overlapping communities near the East Coast, and the reason why that is because there were different airlines. So I'll go ahead and wrap up here since I'm kind of running out of time. But the local flattening ratio and the K fulfillment and the global flattening ratio here were also really interesting to us. And the reason why is that we were able to see that airports, just because some of them had a higher degree. Let me fix this out. They might have had a higher degree, but similar ones with higher degrees. If they were really close to other airports, like on the East Coast, they had a very low flattening ratio. But things like Denver, an airport like Denver would have a very high flattening ratio. Dallas Fort Worth had a high flattening ratio too, because it actually flies to its nearest airports. All right, and the one we're playing with these days that we don't have a lot of answers for is congressional networks. So we can see who's cooperating with who. And you can play with that as well. We haven't gotten too far with that, but it's really exciting. Okay, so from there, I'll go ahead and wrap up and conclude. So just thank you so much. You can visit all this software and some of our infrastructure online, join our Google group. And so today we described a few new descriptive metrics. We are developing some new software and techniques for analysis. And our next steps include modeling. And we'd love for you to keep in touch with us. And thanks to the whole team who's worked on this project. It's been really great to work with them.
Excellent. Thank you, Clio. Thank you so much.
Thank you.
Exciting case studies, and also for demonstrating the software. That was great to see live, and sticking to the time, managing to do all this together. So we have around 15 minutes for discussion and questions. Nick asked the first question, which has to do, I don't know if you can see it, about the disciplines and communities researching these kind of areas, and whether you have shown the results to them, for example, the Mafia data and the food banks, and whether they had any insights from your research or any additional knowledge.
Thank you. That's a really great question. So what was really fun about working with this is we worked with like Dan Della Posa. He's a domain specialist and he's an expert on the Mafia. So it was really fun for us to find some results and then ask him why that was happening. Like when we found all the people who were going to Miami, he said, why is that occurring? And he was able to tell us. What was interesting to him was finding out that some of the bosses lived on the water there. He kind of was able to glean some stuff from that. And I think that Dan is on our advisory board for this, and he is, from what I know, integrating this software into his teaching. So that was something that was what was helpful for him. Regarding the food banks, Jamie is definitely still in touch with the Thrive Network, and she has gone back and given some of our results to them. We're still working with that network, but it's been really great. So that part we haven't gotten feedback from yet, but it's ongoing. It's a good question.
Cool. Thanks, Clio.
Yeah. Thank you.
I have a question. There's another question about training. We can revisit this towards the end. I have a question about your concluding slide where you mentioned small social networks. Some of them looked quite large to me, so I don't know why you put this qualifier there, and how do you define small versus large, etc.
Yeah. So, well, we have small versus large. Our online software can't handle big spatial networks. So a lot of researchers deal with Facebook friendships. So you have millions and millions of nodes. A lot of our geo network analysts deal with origin destination data, which is really, really big. And then there's some people who do mobile phone data, which is also big, and then other types of social media data. So what I mean by small networks is networks where you can sort of tell a story with a domain specialist, and you can learn about why something is occurring and not necessarily just report the results. I spent a lot of time saying like things like, oh, Texas is connecting with Kentucky more than average, more than we thought based on a model. And it's like, well, why is that? We don't necessarily know. Sometimes you can go back and be like, oh, there was a football game that weekend, or they were going to South by Southwest in Texas or something. But it was hard for us to tell a story that way. And so we do say that these are a bit smaller, but maybe we can find a better word for that than small.
No, I was just wondering if you had a metric as well, as how you define small and large, and what is the limitation, for example, of your software to cope with the larger ones.
We tell people that if it's over 1,000 nodes, you may want to do the R package or something different. But we don't necessarily tell people how many edges it'll
Right.
have.
Okay. Okay.
That
No,
can
this is
vary.
fine. Yeah. I mean,
We
I
haven't
like the
calculated
idea.
that value yet.
Yeah, I also like the idea of this storytelling element rather than throwing graphs and maps at people without kind of being able to then explore them a little bit. And the way I saw it and the way you were having these different windows and kind of interacting with them and at the same time receiving some explanation from one window and interpreting it with the other reminded me a bit of the early days of space-time analysis in geography, when the numbers were relatively small and you could actually follow up and tell a story. And now as the data becomes massive, it's this kind of statements you mentioned earlier.
In the two case studies I showed today, one is the one in the 1960s is pretty nice, and we might be working with one in the 1800s because you don't have the privacy issues you have today.
Right.
If you're looking at people, relationships from a long time ago. And the other one is nice because we can go back to the organizations and say, hey, one recommendation we had made erroneously, so it's good to talk to your domain specialist, was really like, oh, we recommend Feeding America should be, should actually move to the center of the network. That would make it more logistically good. And well, they can't do that because they have this whole other, have this whole other clients on the other side.
Right. I have asked people to post questions on the chat box, but before I get to the other question that is sitting there, I wanted to ask you, since you mentioned privacy issues, I mean, it's complicated enough to try to mask geographical data. Now you are imposing on it a kind of social network data. So what sort of privacy implications do we have here?
Well, we don't track anything with online software. The online software is not guaranteed privacy in any way, just because it's kind of free and online. So if you do have sensitive data, we recommend that you take it offline and do some research when you're not on the internet. In terms of adding the geographic component to already sensitive data, we haven't come across that in our studies just yet, but we do want to be able to do that, to learn a little bit more about what an ethicist would say and what the person who collected the data would say and how to protect the people, maybe by making things anonymous or jittering, etc.
Yeah. And in one of the examples, it was organizations anyway, so this is less sensitive. And the other one, as you mentioned, was the Mafia, which is from years ago. But I can see some implications as we come closer to the present day. And Hannah is asking about training opportunities. And I was checking online, and you have made available quite a lot of material there. And as you said, it's open source software, but maybe you want to say something about what else other support you make available.
We are here to Zoom into your classes, to talk with you if you want to use any of these materials in your classes. You can consider us like consultants. That's part of this research, and we'd be really happy to do that. We encourage people to contact us. We've told a lot of people that they can, and we haven't had a lot of people take us up on it. So if we seem very excited when you do that, we would love to just talk. We'll just talk to you, and we'll walk you through our QGIS tutorial if that's helpful, through the R tutorial, and through the SNoMaN tutorial.
Oh, this is excellent. Yeah, I saw the tutorials. I didn't have the chance to go through them carefully, but yeah, they look quite straightforward to follow. So there's a source of material there, but it's also good to know that we can contact you in person. And
please do. And we'll ask for some feedback from you as well, perhaps.
Excellent. Yeah, it looks like a very promising tool and fascinating. And as I said, the storytelling element is very promising. Any other questions? Anyone? Okay, I don't see any questions on the chat box. And Nick, thanks for supporting us as well with the webinar. So So unless there are any other questions, I would like to thank you again so much for your time and presenting fascinating research and also the tool and demonstrating it to us, because usually we see screenshots, etc. But it's great to see that the actual thing actually works.
It worked mostly, so thanks for bearing with me.
It works really well. It was actually very fast as well and very intuitive the way you demonstrated it. So thank you very much. Thank you, everyone. And I would like to wish you a good break during the season. And we will be with you next year sometime with another webinar. We haven't decided the speaker or the exact date yet, but stay tuned with us. Thank you.